In this video, we construct some interesting maps between different counter sets with applications to the Coarea formula. Suppose we have two different counter sets but constructed similarly in the sense that the number of subintervals at each stage are the same. So we have 4 and then 4 again here. If we end up with 8 in the next, we will have 8 in the other one. Now, an interesting universal way to construct a bijection between this counter set to the other one would be just by saying that at every stage, when we move to later stages, we can just number them. So this is first component, second, and so on. If x is in the kth subinterval, we know that x should be in one of them because it has survived these subdivisions at stage n, then f of x is in kth subinterval at stage n of construction of D. And by the very way we construct counter sets, this will uniquely tell you where f of x is, because you can zoom in to find x, and you have to use the same collection of nested intervals to find f of x. So this uniquely defines a bijection. Of course, it's invertible by the same process. Given f of x, there is a unique sequence of subintervals that zoom in on f of x and find the same back here in the domain. So, but in fact, this bijection is homeomorphism, that it is continuous and its inverse is also continuous as well. Well, maybe this last part needs some more argumentation, but that will not be the main topic of my presentation today. What I'm interested in is finding Lipschitz maps between counter sets. With Lipschitz maps, recall that Lipschitz maps cannot increase Hausdorff dimension. So that's an obstacle already there, that you cannot do Lipschitz function between arbitrary pair of counter sets. The target has to have a smaller dimension or equal to it than the counter set in the domain, but of course it can be strictly smaller. For example, the constant map kills the dimension. Okay, so this is really just one example, not a universal one, but again, just like the counter sets themselves, once you see this example, you can work on many variants. And the example that I'm going to talk about is from a thesis, a PhD thesis that I have benefited a lot from in my research. The example is from the doctoral thesis of Rachel Lawrence Philip from the University of Zurich. So ETH Zurich. This is available online for free. and the title is the Coarea formula for metric space valued maps. It's just saying that functions that go from Rk into a metric space and not necessarily a Euclidean space. But anyway, the example I'm talking about is from chapter 6, where they want to prove that some assumptions in the Coarea formula are actually necessary. And you often counterexamples are more illuminating and satisfying to see than main theorems, which take tens of pages to prove. Okay, so the construction starts by fixing a counter set, a fat counter set. So inside the interval 0, 1 with h1 of this equal to 1/2, precisely half of the measure of the interval. And we saw easily how this can be achieved and why such sets and their existence is no surprise at all. Okay, what then we do is we define a function from R to R by gamma of t to be the Lebesgue measure, which is equal to the h1 measure of the part of counter set up to t. So gamma of t will be how much of complement of c lies before t. So nothing special going on here. So your counter set is somewhere here. We know that it's totally disconnected. It doesn't contain any interval, but magically it does have a significant measure, in this case equal to 1/2. And the function gamma, what it does is, so you take this t here, and then it looks at this part. Of course, the part before 0 is not there. You could just put 0 here. And we check how much of the complement of C picks up from that part. C is a compact set, so its complement is measurable, so everything here is well defined. And again, H1 is just the Lebesgue measure by stuff that we have done on Hausdorff measures in my previous videos. This is not new. Okay, what can we say about this function, gamma? Gamma is increasing. Well, if t increases, you have a bigger set and measures never go down. And that's completely obvious. The other one is that gamma is 1 Lipschitz. And even if you don't know what 1 Lipschitz means, you can figure it out from the formula I'm going to write. So gamma of t minus gamma of s, which is a positive number, of course, if t is bigger than s. Okay, very cool. So this will be, t is there, and s is here. So how much more measure do you pick up here? So that's the difference, gamma t minus gamma s. Again, by measurability, it's not trivial, but by measurability, that's why you can cut out easily and have additivity and stuff like that. But this is nothing other than the H1 measure of a complement of C intersected. So again, without loss of generality, I only need to consider between 0 and 1. After 1, the function gamma actually becomes constant. So this will be from S to T at most. And even if this complement was all of this interval, that would give us only a measure equal to T minus S. I can put this here, but we definitely know it's strictly less than that much, but we don't care. So what we have here is that for every pair, gamma T minus gamma S is less than 1 times difference in the argument, which is exactly what being 1 Lipschitz means. So why is being 1 Lipschitz important? Because we have differentiability. And that is also something we have talked about before, and it's called Rademacher's theorem. A gamma prime exists almost everywhere. Lebesgue almost everywhere. At almost every point, gamma is differentiable. Okay, the main claim, the non-trivial claim we will have, is that for almost every t in the counter set, gamma prime of t is actually equal to 0. Now let's see intuitively why this is the case. Okay, what part of this, let's go back to definition of gamma t. So gamma increases when you pick up more stuff from the complement of C. So if C, again, this is not true because C contains no interval, but if C contained this full green interval and you were here with this T, increasing T for some time, going to T plus epsilon, would not add anything new to this because everything is contained in C and no part of complement is picked up by moving from T to T plus epsilon. And therefore, gamma is constant in traveling from T to T plus epsilon. This would be precise if indeed C was like this, had a full line segment in it. We know that that is not true, it's totally disconnected, so this gives us an idea of why the claim is reasonable, but it's far from being a proof, given that actually C has no intervals in it. But this proof is quite nice. Okay, suppose gamma prime of t exists, which happens almost everywhere by Rademacher's theorem again. Then we have this easy calculus formula that well, usually the derivative is defined by comparing gamma t plus h to gamma t, but also there is this double-sided version. So let's switch to h. Gamma t minus h, but then you have 2h down here. So if a function is differentiable, you can also recover the derivative from this quotient. And what is this equal to? We saw this formula up here when we compared gamma of two values. And therefore, this will be h1 measure of the complement of C intersected with t minus h, t plus h. So the symmetric interval around around t. Now we need another fact from measure theory that almost every point in a set is a Lebesgue point of C. This concept now is totally new even on this channel. What that means is that for a point to be a Lebesgue point. So what happens at the Lebesgue point? If T is a Lebesgue point of C, it means that the balls around T, so we are in dimension 1, it's just like this, pick up almost all, so C picks up almost all the measure in this interval. So that h1 of this divided by the measure of the ball, which is 2h, as h goes to 0 is equal to 1. So for every measurable set, almost every point has this property. And in pictures, it's saying that the set C almost fills up the entirety of this interval from measure theoretic point of view. So maybe for this interval I drew, it's 90% of the interval is in C. And when I go smaller, then this improves 99% of the set. 99% of the interval is picked up by C, and in limit it becomes 1. So almost every point in C, just from C being measurable, has this property. So if in this previous calculation we only assume that gamma, sorry, that's the theorem, we only assume that gamma prime exists, if we further assume that T is a Lebesgue point of C, then that means almost all of this interval is picked up by C, which then leaves nothing for the complement. So if T is in C is such that gamma prime of T exists and T is a Lebesgue point, then continuing the calculation from above, this becomes limit as h goes to 0 of 1 minus h1 of C intersected with T minus h, T plus h, divided by 2h, but now that goes to 1 minus 1 equal to 0, and we have completed the proof of the claim that at almost every T in C, gamma prime of T is 0. Okay, now there are two ways to visualize the function that we have constructed. One of them is to draw, I would need both of these descriptions. So C is somewhere, magically it has positive measure, but it's totally disconnected. And then this gamma goes from 0 to 1/2. Actually, gamma, yes, never goes above this much, because if you go to the end of the interval, if you take T equal 1, gamma of 1 becomes h1 of just complement of C, which is 1 minus h1 of C itself, but that was 1/2, so this also becomes 1/2. So 1/2 is the maximum it achieves. At 0, of course, you pick nothing from the complement. So at 0, let's write some of these values. At 1, this is 1/2, and this is the same for any x after 1 as well. And this is gamma of x for all x negative. And this is a continuous function, actually, because it's 1 Lipschitz. And then gamma prime of t is 0 almost everywhere on C. Another claim about this gamma is that gamma is injective. No two values, so if t is bigger than s, then gamma of t is also strictly bigger than gamma of s. We already know gamma is increasing, but now we prove that it is strictly increasing. Well, this is easy because between there exists some interval which is contained in ST and also completely in the complement of C. So we know that complement of the counter set is an open set and with arbitrarily small intervals. So between any 2 points, you can either there is no point from the counter set, then you can take the full interval to be a b to be just st, or there are 2 counterpoints, in which case there is some gap, some interval in between. In any case, you can find this. Then it easily follows that gamma of t minus gamma of s is at least equal to b minus a, because at least this much new measure you pick up in increasing t from s to t. Okay. Now already we see now we have an interesting example, because we have a function that is strictly increasing and gamma prime is 0 almost everywhere on a set of positive measure. So informally we can say you increase without paying any price in derivatives. And that brings me to the other way of visualizing this function, gamma t. So because this is going from R1 to R1, we can draw them in the same plane. So gamma t starts at 0. At the end of the interval 1, it will reach this point. So at 1, it will be 1/2. And then it's strictly increasing. And every time you hit counter set, you have 0 derivative. And I have no idea even how to draw this. So it has a lot of, on a set of measure equal to 1/2, at least, its derivative vanishes. Okay, so the last use of this example will be a counterexample to the Coarea formula. And even if you don't know what Coarea formula is, it will be apparent from the calculation that I will do. So the example we built, to visualize it, you have to go back to this separate copies of R1 And then here you have this fat counter set C, which is mapped to a counter set with measure 0. By the way, you can use area formula to see that gamma of this C is equal to gamma prime of T on C, because F is Lipschitz, because gamma is Lipschitz, this formula is valid. So measure of image of this equals to that, but this is 0 almost everywhere, so it's 0. So definitely this counter set with measure equal to 1/2, this fat counter set, must have been crushed by this gamma to a 0 measure counter set. Okay, so this fat counter set C maps to a thin counter set. I don't want to get into the details of why image of gamma itself is a counter set. You're welcome to ask questions in the comments or even discuss them between yourselves. Okay, so the example which will fail the Coarea formula is rather fake, because all you do is you multiply by the unit interval. Now you have a subset of R2 with positive area. So I want them to be equal size, but forgive my inaccurate picture. So H2 of C multiplied by the unit interval is positive. Now what happens here is different, so you have a null set multiplied by the unit interval. Now you want to find the function between them, and that will be f of x and y goes to gamma of x and y. So again, I emphasize that this is rather fake example just to make numbers work. So a line like this, everything on this line maps to the line at the same height. So if y is fixed, that's what the picture is showing, but the x is mapped by this function gamma. Okay, and f now is a function from this space, this subspace of R2, into this other space with whatever Hausdorff measure it has. Okay, it's easy to check that derivative of f at every point is nothing other than 0 and identity here. So in the x variable, the partial derivative with respect to x is 0 because x belongs to C, and if you freeze x in the vertical direction, it's identity map, so its derivative is also identity map. So the Coarea factor, this Jacobian used in the Coarea formula, equals 1 almost everywhere. Well, this is also almost everywhere because gamma prime is 0 almost everywhere, not at every single point necessarily. So integral of this Coarea factor, so we will look at the Coarea factor as if it goes from dimension 2 down to a one-dimensional object, as if it was one dimension. So we want to show that Coarea actually fails. So we want to show necessity of being one-dimensional. So we're saying that if it's not one-dimensional, it fails. So if the Coarea was going to hold, we could treat this as if it had one dimension, dimension 1, and then we would expect the following to hold. So on the space in the domain, if you integrate this Coarea factor of the derivative with respect to L2 measure, then this would be the measure, H2 measure, or L2, the same, of C times I, which is equal to 1/2 by Fubini. And the Coarea formula is you integrate over your image, so D times I, with respect to H1 measure, and then here will be H2 minus 1, so which is again 1 of the pre-images of points intersected with this space domain. But then this is, I claim, equal to 0 because F is bijective. Because gamma is bijective, it's easy, immediate to see that why this is bijective as well. So that the pre-image of a point is actually just a single point. So its one-dimensional measure is definitely 0. So this is integral of 0, so it becomes 0. And we see that this does not match here, so Coarea formula fails. And this shows that, of course, we know that the Coarea formula is true for Lipschitz maps from any measurable subspace of R2 into R1. We know that Coarea holds for such maps. The reason it failed here is because you're not mapping into R1, you're mapping in this uncountable copies of R1, basically. And that makes this space really huge from the point of view of H1. And then this counterexample shows that you cannot maintain validity of the Coarea formula any longer. And just a quick point on bijective, this, if you take a point here, first of all, the pre-image must be somewhere here, but then if this is kind of gamma of x, there's only one x mapping to that because gamma is bijective. That's why here F inverse of y is just a singleton. Okay, so even if you, the last part was kind of a little bit relying on the assumption that you have watched my Coarea videos, the initial construction is still very interesting and has been used a lot in analysis to find counterexample to many things. There are also variations of that. I hope at some point we will talk about Cantor functions, which are kind of similar, except that instead of looking at each one of here, you look at h of the right dimension, and here you don't put complement, just the set itself. So hope you did find something to take home from this video. Please put your questions and comments in the comments. Until next video, have a good one.